Okay, this lesson is about voltaic cells. In spontaneous redox reactions, electrons are transferred and energy is released. We can use that energy to do work if electrons are made to flow through a wire the way they do in batteries. Batteries are electrochemical cells which are harnessed to do some kind of work. If you force electrons to pass through a wire, you can make the wire get hot, so that you would get a heating element, for example, as you would on a cook stove. On the other hand, you could make the electrons pass through a coil and they generate a magnetic field so they can run a motor. So we harness batteries to do all sorts of things, and batteries are essentially electrochemical cells. In a voltaic cell, reduction occurs at the cathode. Cations are attracted to the cathode. When they come to the cathode, they pick up electrons, and we remember that gain of electrons is reduction. And I also remind at this point that there's a mnemonic you can use. Leo says Gert. Loss of electrons is oxidation. Gain of electrons is reduction. The salt bridge in a voltaic cell, portrayed over here, helps to equalize the charge imbalance that occurs as new ions are released into solution or as the ions are taken out of solution. So what the salt bridge does is maintain the charge balance. Without the salt bridge, the electrochemical cell cannot rebalance the charges and the reaction will stop. Cations move towards the cathode, anions move towards the anode. That's the one thing I would ask you to memorize. Cations are attracted to cathode, anions are attracted to the anode. How do we attract a cation? A cation is positive. We attract a cation by having a negative charge. Negative is attracted to positive. In the cell, electrons leave the anode and flow through the wire to the cathode. So it always goes anode to cathode. Normally you draw the anode on the left, cathode on the right. Good way to remember it, A to C. It's alphabetical, anode to cathode. In the cell, electrons leave the anode and flow through the wire to the cathode. Electrons flow from higher potential energy to lower potential energy from anode to cathode, just like water flows from high to low. So the anode is the higher energy half reaction, and it drives the other reaction to take electrons. In this example, drawn from Brown, chapter 20, number 3, we see two reductions. The reduction of the Nicholas ion and the reduction of the ferrous ion by the addition of two electrons. Both of them have negative reduction potentials, which indicates that the reaction is actually likely to occur the other way around. So it's more likely for nickel to undergo oxidation, for iron to undergo oxidation. So how do we pick which reaction is going to go forward and which one's going to go backwards? What we do is we take the one that has the larger number, in this case the reduction of iron, and we flip it so it becomes positive. Or we can flip both of them, pick the one that's more positive. The one that's more positive is going to drive backwards to the one that's less positive. So in this case, if we flip both of them, 0.44 has a higher potential than 0.28. So this reaction will drive this one backwards. And then we can write them in the correct way. So we see that the iron one is acting as the oxidation. This one is acting as a reduction. And how do we calculate the total voltage of the cell? E naught reduction plus E naught oxidation gives you E naught of the cell. And we see that the nickel is accepting electrons to become metallic nickel. Metallic iron, on the other hand, is giving up electrons to become the ferrous ion. The 0.44 is added to the negative 0.28, you get a total of 0.16. So this electrochemical cell generates 0.16 volts. It's not a very efficient reaction for use in a battery, but it's actually the reaction that was used by Thomas Edison to do experiments on when he was inventing the light bulb. It was called a knife battery because it used nickel and iron, NiFe. Here we have the cell portrayed. We have a solution of ferrous ions or some other suitable electrolyte with a metallic iron electrode inserted into it. So that part is the part that's reacting, the part that's out of the solution obviously can't react. It's got to be an electrode that conducts electricity, obviously. The nickel electrode is also inserted into the solution, and we have a salt bridge to allow the potassium nitrate ions to equalize the development of an imbalance of charge. Electrons move again from left to right, from anode to cathode. This is called the anode. At the anode, the anions are oxidized. At the anode, where the metallic iron loses electrons to become ferrous ions. We portray that here. We show the iron. After the iron metal gives up its electrons, it becomes positively charged, and it goes into solution. Then that plus charge that's generated has to be balanced by the movement of nitrate anions into the solution so that you don't develop a charge imbalance. So as the reaction proceeds, the anode gets lighter. This electrode gets lighter as the reaction proceeds. On the other side, at the cathode, cations are reduced at the cathode. So because there's an abundance of electrons being pushed into this electrode, it attracts the positively charged nickelus ion, which deposits onto the metallic nickel, and it also itself becomes metallic as it acquires electrons. So this electrode gets heavier as the reaction proceeds, and that's the half reaction portrayed here. The cathode gets heavier as more metal is deposited. The net voltage, because one reaction is driving the other, is 0.16. So it's not a very efficient reaction, but it does occur.